Hello. So for this first lecture for Gen Chem 1, Chem 1211, we'll jet through kind of the history of atomic theory and where we got to mostly how we look at things today. I want to caution you that I want you to have the background here, but I don't intend to ask you historical type questions like you probably will not see on any of my exams a question that would have these researchers as options on a multiple choice exam. I'm probably going to more likely give you conceptual type questions and say work this problem out or figure out what the structure should be here or something like that. The context is, however, important so that you follow how we got there, and it gives you a broader basis for the stuff that we're going to be talking about throughout the rest of the course. So we'll go back as far as ancient Greece here to think about how folks were thinking about the world and what they called elements back then. So you have probably been exposed to some of this, maybe in some literature stuff, or especially if you've read any Greek mythology or stuff like that, and actually maybe an interesting other scenario where you might have been exposed to this and not realized it. So this is the whole idea of Earth. Here is Terra in this diagram, but Earth is denser than water. They have another sphere for water here. Air is the next, and then fire is the least dense. So it would be the highest stratigraphically of those four elements: Earth, water, air, fire. So yeah, this is kind of the ancient Greek way of looking at it. And Aristotle lays out this idea. I started to call it a theory, and I kind of paused there, but I think it's correct to call it a theory, even though it was the incorrect theory. So the problem is that it's Aristotle, and so we listen to Aristotle so much, or we did for so long, that it essentially handicapped us for 2,000 years because, well, Aristotle said, so it must be correct. And it turns out it was not. We've got to be willing to challenge things, even if they're written by Aristotle. So this is an incorrect model. Interestingly, if you've heard maybe in history class in high school or something like that about Benjamin Franklin flying the kite with the key tied to it, so there are some hints that what he's doing is actually this sort of thing that we call alchemy. This earth, air, fire, water theory is the alchemy theory, and he's standing here on Earth, and then so it's raining. So now you have a differentiation of the elements where the water phase is falling out of the air phase, and he's thinking that there's then a further differentiation of the lighter fire phase up higher. And so he's flying his kite up, trying to get past the air phase into the fire phase, and that's turns out to be lightning and electricity and all that. So he got some results, even though he was working off of a flawed theory to start with. And this theory gets really deep with phlogiston, a lot of other shenanigans, trying to explain the shortcomings of the theory. And we still do stuff like this today. We'll hold on to a theory and we'll make shenanigans to try to keep it, even though we should be willing to let go of it and go to the next thing. And also, I said the next thing, but it turns out that it was coincident in time. There was a guy arguing with Aristotle about this whole earth, air, fire, and water is everything idea. This guy named Democritus. I often mess this up because Democritus sounds so much like democracy, And so I think this is the guy that came up with the democratic system, but that is Demosthenes. I actually had to change my PowerPoint because I had the wrong name on it recently. But Democritus is the guy apparently that was arguing with Aristotle about. He said, no, it's these little atoms, atomos things. And then much later in the 1800s, this guy, a school teacher actually, a high school teacher named Dalton, kind of resurrects Democritus' idea of these atomos. As his idea is, if you take a thing and you divide it, you've got a smaller unit of the thing, and you divide it more and even smaller and even smaller and even smaller, and then there is a limit as to how far you can go down, and you get the fundamental particle of that thing. And so these little hard spheres that Dalton envisioned are what he calls the atomos, the indivisible particles of those things. Now, that's not a perfect theory yet either, but it's better maybe than everything being composed of some mixture of earth's airs, fires, and waters. So it is an evolution of the theory. We're getting a little closer to that. And so Dalton's atomos theory almost works, at least for elements. We'll see how it does not work for compounds. But for elements, you can say we've got, now technically pennies no longer are solid copper, but just go with me on this. Let's assume that an old school copper penny is made entirely of copper. Well, so you could divide it into a half a penny or a quarter and keep going down. You zoom down to this atomic level where the copper, pure copper, consists of just a lattice of copper atoms. But if you can break off one of these copper atoms, well, that's it. If you go any further down, we're going to talk about that, but if you go down any further, we are no longer copper. We are in a totally different realm of matter at that point with subatomic particles. But a single atom of copper is still copper. So this gets to the idea of now what we've replaced Aristotle's earth, air, fire, and water. That was his 4 elements. But now we say that there are a bunch of elements, actually about 90 naturally occurring. I say about because there is now some new, as in the last 10 years, controversy about what we're going to call naturally occurring. But the traditional thing to say here is that we have 90 naturally occurring elements. And there are plenty more than the naturally occurring ones that we create in nuclear reactors and stuff like that. So if you look at your periodic table, well, that's your list of elements. And it grows. We add elements onto the bottom of that table. Now, you're not going to shove any new ones in the middle. We're done with those. We've got them all worked out now in the middle, but now we keep adding to the end by creating heavier and heavier elements along the way. Also, I would note from that previous slide, elements, y'all do make sure that you are reading your text to go with this. I am not trying to make sure and tell you absolutely every detail about things. That last slide had on there the definition of elements, and you probably need to have that in your head. Again, I don't intend to ask you memorization type questions like regurgitate the definition of an element, but you do need to understand what an element is as contrasted to what a compound is. So a compound, we're going to say, instead of the definition of an element, which is you can't divide it down any further, you get down to the atomic level, that's still, in the case of copper that we used, it's still a copper atom. But with compounds, that's not the case. So here we've got copper 2 oxide. I'll tell you later what the 2 is about. But it's a compound of copper. So you have a copper atom and an oxygen atom bonded together, and they create a different kind of lattice than the copper lattice we saw earlier. But now if we divide it down, we get to a point where you can't divide it down to single atoms because somewhere along the way you already lost some of the properties that make copper oxide, as opposed to elemental copper. So it's a different thing because it is two different elements in some ratio. So reinforcing again this idea that you do need to read. Page 69 here for OpenStax means in my PDF version of it. You can download a PDF of that thing, or you can look at it online. If you're looking at it online, I think there are no such thing as page numbers, but you can always just Control F or Google to find it. Conservation of atoms. So this is going to be a really important idea in this course, is that with the exception of our Chapter 21 stuff when we talk about nuclear processes, with the exception of nuclear processes, we're gonna abide by this conservation of atoms idea. So this posits that for chemical reactions, or for any kind of chemical change, it would apply to physical change also, but that one's even more constricted. But absent nuclear change, you cannot destroy or create new atoms. So here's how this affects you. If we know that there are a certain number of copper atoms in the universe, that number of copper atoms, absent nuclear processes, does not change. So if you have a certain number of copper atoms in a chemical reaction, the number of copper atoms that you start with will be exactly the same as the number of copper atoms that you end with. But what happens in our chemical reactions is that you rearrange them, like in the previous slides where I was talking about having those oxygens making a different lattice. And so that first lattice with just the copper atoms makes a different material, has different properties than the other lattice that has copper and oxygen in a certain lattice. So that's going to be really important to how we look at chemistry going through this course. So in the 1800s there, what motivated Dalton to look for this, let's get out of the Aristotle trap thing. So there was a lot of experimentation going on in the 1800s. So we're starting to see, well, look, if we take this copper to oxide and we digest it and we can tell how much of this oxygen stuff is there and how much of this copper stuff is there, copper to oxide always turns out to have the same ratio or proportion of copper to oxygen. And so that's what this idea is, this law of definite proportions. So all samples of a pure compound contain the same elements in the same proportion by mass. So example I have here is isooctane. So think of octane like the octane rating in fuel. So if we were to digest that, look, it turns out that octane consists entirely of carbon atoms and hydrogen atoms. And if we take these three different samples, obviously these samples are going to be different masses of sample to start with. Sample A has 14.82 grams of carbon and 2.78 grams of hydrogen, and then different masses for these. But here's the thing. If we ratio them, so this 14.82 grams of carbon for every 2.78 grams of hydrogen turns out to be 5.33 grams of carbon for every 1 gram of hydrogen. And this new sample here, B, well, when we divide it, look, it's exactly the same, 5.33. This third sample, also 5.33 grams of carbon for every 1 gram of hydrogen. And so that's the experiment that led us to thinking about this definite proportions idea. So octane always has that same ratio by mass of carbon to hydrogen. So unfortunately, in chemistry, we are very confusing sometimes. I don't like what I'm about to say here, but the rest of the chemistry world doesn't care that I don't like it, so we got to go with it anyway. All right, so we had the law of definite proportions. Octane. Octane always has the same ratio of carbon to oxygen by mass. Now there's another principle that we have of law of multiple proportions. I wouldn't have named it that because I think it's confusing. So we have the definite proportions is for a given named compound, that mass is always the same. Multiple proportions says, now if we have something other than octane, this is octane, definite proportion, but if we have some other thing other than octane, like methane, well, methane is not octane. Therefore, it has a different, or it can have a different ratio. If it were octane, always the same, but methane has a different ratio. We find that it has 3.75 grams of carbon to 1.25 grams of hydrogen in this 5-gram sample that I have here. So if I divide those, then I come up with 3 grams of carbon for every gram of hydrogen. Well, let's take another sample of methane and let's check it. 7.51 grams. That's a different amount of methane to start with, and sure enough, it has 5.63 grams of carbon in it and 1.88 grams of hydrogen. But again, if I divide those to get a ratio, I will find law of definite proportions applies that it's still 3.00 grams. Okay, but here's the part that I want to make sure doesn't confuse you. So law of multiple proportions says that different compounds can have different proportions. The law of definite proportions says that for a given compound, the ratios will always be the same. All right, back to our development of theory here. There's a nice video discussion of the Thomson experiment here. There's a little bit of simplification to it. Just be aware of that. So we're still in the 1800s here, late 1800s now, and so we're starting to actually. Thomson is looking at electrons, but he doesn't know really that they're part of atomic structure yet. But it did lead us into that. He's looking at this voltage that's applied. They're starting to work with electricity, even though they don't know what's going on yet with it. These beams of electrons fire off of a charged metal surface through another charged system, and you have this vacuum tube here. And so what Thomson is doing is he's deflecting it. So get it deep into the physics here, and it will deflect based on how much charge you apply. The more charge you have, the more deflection you have, but the more mass of particle you have, the more it resists, the more momentum it has, and so the more it resists the deflection. So you can use that to try to determine the exact deflection angle that you have. And then Millikan takes that idea further. And so what Millikan is doing, his oil can experiment, everybody calls it, is what's happening is he's got this vacuum chamber set up, and he's spraying oil into it and applying these voltages so that it's stripping the electrons off. And so the electrons are falling towards the bottom, but then he's got a negatively charged plate at the bottom and a positively charged plate at the top, and he will change the amount of charge that he's applying to these plates and basically make the electron, well, it wasn't really the electron, it was a drop of the oil with electrons on the surface. And so he's making these drops hover by applying a charge, basically electrically levitating them and watching them and checking how much voltage he has. And then he used some maths to figure out how many electrons are on that, and worked out the electronic charge, because it turns out that there's always a multiple here of the same number. You always get this 1.6 times 10 to the negative 24th coulombs each time you jump here, and so it works out. He could calculate the mass of the individual individual electron. I don't expect you to be able to replicate Millikan's experiment. It's a fair bit of physics actually to do that. I just wanted to give you that background to give you when I'm going to tell you this chart that gives us the mass of the electron. Well, that's where it comes from. It comes from experiment. So Thomson developed a model. He's like, well, okay, so I've been playing with these electrons. And now Millikan's gotten us a mass for one of these electrons, and these electrons are apparently like shoved in this drop of oil, and so I think that kind of leads to this idea of, it's usually called the plum pudding model, but it's the Thomson model. Apparently plum pudding is a thing in Britain, and I've never had it myself, so I don't really. Apparently, it describes pretty well what they were thinking. Is there are these bits. I don't know. I think of them as raisins, but that's not plums. I don't know. They're just kind of distributed in the mass. So you've got this atom thing that nobody knows what it is yet, and you've got these negatively charged bits. What turns out later to be the electrons. It's just randomly in this background mass. So that's Thomson's model, or sometimes called the plum pudding model. So let's think, what might happen? What might happen if you were to, let's say, fire a particle at this mass of stuff, right? So the thought experiment is, well, let's see, what would happen if we take this and we fire it through? Well, it's got this differentiated mass here, a little bit different, but it's still homogeneous. So it would probably sometimes make it through, maybe not always, maybe deflect around these sometimes, but they're pretty homogeneous. So probably it would just act like a sponge and sponge some of our particles going through. So this guy Rutherford says, "Oh, hey, cool! That sounds like a cool experiment. Let's do it." So he gets this really thin gold foil, thinks he knows how many atoms thick it is, and he fires this beam of what are called alpha particles. We'll learn in the nuclear segment that that's basically a helium nucleus, but just call it an alpha particle, it's fine, and just think of it as a very tiny particle. And he fires it at this gold foil. Now, he's expecting it to just be sort of absorbed, depending on the intensity of the beam, and so this is the idea of setting up a model. So Rutherford has a model, Thomson's model of the atom, and he makes a hypothesis for what's going to happen, and he runs an experiment to try to confirm that. Now, here's the neat thing, is that it didn't do anything like what he expected. He had his model, he had his hypothesis, good science going on. He fired the alpha particle at it. His comment apparently at the time was, "It is as if I fired a 15-inch shell at a tissue paper and it reflected back." What happened was that usually, I think I have a graphic here, usually the particles went straight through. Occasionally they were somewhat deflected, which is a little bit confusing from the old model. Shouldn't get very much deflection like that. But then here's what Rutherford was really reacting to. Occasionally, a very small number of these basically hit and bounced off. And that doesn't make any sense with this plum pudding model. So Rutherford had to go and come up with an entirely new proposal for what's going on. It's not the Thomson plum pudding model after all. So what Rutherford comes up with is, okay, let's see, what if our atom is basically this dense little tiny area. It's got all this mass shoved in it, and then our atom is mostly empty space with all of the mass crammed down into this central area. We'll talk about those units in a second. with the electrons in this cloud around it. And so you have something, I think, that might look a little like our solar system, with the sun pinched down at the middle. Most of the mass in the solar system is in the sun. Most of the mass by far most of the mass in an atom is in the nucleus. And so if you think of an atomic radius, so let me change this and draw on it a little bit here. So the radius being like out here, right? So if you think of that radius as being about 100 picometers, 1 times 10 to the 10th, negative 10, the nucleus itself is right here in the middle, and it is only 0.005 picometers out of 100 picometer total radius. So that's what Rutherford's new model says, is that, look, where the mass is, where this nucleus idea is a tiny, tiny volume in the center of the atom. And then, so we will basically use that model of the atom. The Schrodinger model is the best we have now, but it gets into the differential equations and modeling things as wave functions. We'll touch this a little bit in Chapter 6, but for now we're going to stay basically with Rutherford's nucleus, followed by Bohr, the guy that really worked on where the electrons are, as our model. We won't go as far as Schrodinger until we get to Chapter 6, and then we'll only do it a very little bit. So Rutherford has this nuclear model that says that the nucleus is like this 1 meter beach ball centered in Dalton, and the atomic radius goes further than almost Marietta. So that's his model. That's what we're going to go with, is that this atom is mostly empty space with a very small, dense nucleus. So some units here. Most of the time you will hear AMUs, and that the acronym stands for atomic mass units. Certainly for this course, you can consider those numerically equal to 1 Dalton. A Dalton is actually a better unit for some pretty specific reasons, really not ones that matter very much. Occasionally you will see them as one. This is a kind of a fancy U. It's a micro, but it's 1 Dalton. Technically, I should say approximately equal to 1 Dalton. They're not precisely the same, and just has it's based on what the difference is on what they're based on, and the Dalton is a better way to measure atomic mass than the atomic mass unit. There's some confusion, physicists, chemists fighting about how we should do that. So let's just stay with the Dalton. If you say AMUs, it's fine. 1.6605 times 10 to the negative 24th is, in grams, is a Dalton. Notice, please, this will probably be a thing throughout the course. I will tend to write stuff capital E, negative 24. That's the same thing as down here, times 10 to the negative 24. It's just easier to write, especially if I'm writing things in Georgia View or some other electronic format. This is becoming more common. You could see it both ways. So, but now I don't guarantee that you'll see that in any course but mine. So just know that. Daltons, if you take somebody else for Gen Chem 2, it's less likely they'll use Daltons. They'll probably use AMUs. Be familiar with both terms. I just claim here, there's a link at the bottom as to why that Daltons is a better term than AMUs to use. And similar to table 2.2 in your textbook. So it turns out, yeah, even your textbook wants to continue to use AMUs. I'm going to say Daltons. There's a better term. I would want these on my cheat sheet if I were setting it up, just in case anything comes up about masses. It probably will. So here we have, look at these mass differences. We have proton. Here's a symbol for a proton. It's P with a plus. 1.673 times 10 to the negative 24th grams. Or you could say 1.0073 Daltons. has a charge +1. All right, so look at this neutron. Very, very slightly heavier. Third decimal place, 1.0087 as opposed to 1.0073. And you know what? Usually we're just going to say 1 Dalton for the proton and 1 Dalton for the neutron is probably all the precision we're going to need on that. But now look at this one, the electron. This is drastically different. Look at this difference in mass here. So 9.11 times 10 to the negative 28. So that's 4 orders of magnitude. It's really closer to 3 because that's a 9 instead of 1. So 3 orders of magnitude, or 1,000 times smaller. So if you were to do the Daltons here, 0.00055 Daltons mass for the electron, you know what? We're usually going to say 0. So 1 and 1 for the proton and the neutron, and 0 for the electron is usually sufficient. But the charge is very important, that all the positive charges tend to lie on the proton, all the negative charges tend to lie on the electron, and none on the neutron. All right, so I mentioned Bohr earlier. So here's what we have. This Rutherford nuclear model leads to the Bohr model of the atom. That's the way it's spelled there. So we're going with Rutherford's dense nucleus. If I use the term nucleons, it just means the protons and the neutrons that are down in the nucleus. So nucleons means particles down in the nucleus. They're tiny, remember, shoved down there. A really, really tiny volume right in the center of the atom. And then we have this, what's called the extra nuclear, or outside of nucleus region. And that's where our electrons are. The arrangement of those electrons, it's going to be really important as we go forward in this course. You see here that I've put 2 sets of electrons. I put a set of 2 electrons really close in, and then the next 4 electrons further out. That would make a carbon atom. So that's going to be important. Why did I put 2 there? Why did I put 4 out here? I could have put as many as 8 in this next shell. So the term shell is going to become important with that. Okay, so chemical symbols. So we have to have some shorthand to write all this stuff. So when I look at this, remember what I talked about day 1, and talking about all those things that run through my head because I've been doing this so long, right? So I see this is lead-208. It tells me a lot about it. It tells me it's ionic. Well, we're going to talk about what I am seeing in this symbol right here. All right, so do use your periodic table. I want you to use that thing so much. It's the best cheat sheet in all of chemistry, I promise. So the letters here, PB, that's lead. I'm not going to ask you to memorize those. If I do something where I don't tell you that, like, you see an abbreviation PB, what is that? And he's asking about lead in the question or something, just ask. I don't mean to do that to you. I don't want you to have to memorize what those symbols are. PB is the symbol for lead. Apparently it has to do with the Latin plumbum for lead, but it's not a Latin course, so you don't have to know that. So the letters are the ID of the element. So PB is lead. We're locked into certain things at that point. So it also, please do remember this, that a certain element always has a certain number of protons by definition. So technically, we wouldn't even need to write this 82 because it is lead. It is PB. Therefore, it must have 82 protons. No way out. We've defined the system such that an element of lead is defined as an element having 82 protons in its nucleus. Now you can write the atomic number, and tradition is to put it down here, kind of as a subscript, but leading before the symbol. Z is usually an abbreviation that we'll use for the proton number or atomic number. It is the atomic number is synonymous with number of protons in. Okay, so then other numbers here. Oh, I'm sorry, I did a little graphic here where I'm going to put 82 protons in that nucleus. All right, so we're going to start to build this little model of the atom up there. Right now, we know that we've got 82 protons. Okay. All right, so what else is going to be in there? Well, obviously we have another number up there, that 208. Now, please, y'all, please. I don't know where this comes from. But I have seen it in almost, maybe literally every chemistry class that I've ever taught. Somebody will try to divide this in half, and please do not do that. It is rarely ever the case. You do not divide this. That number, 208, is the mass number. Now, thinking back to our table, we're simplifying here, and we're saying that protons have a mass of 1. Neutrons also have a mass of 1, and electrons don't count. We're going to call their mass 0 right now. So if protons are 1 and neutrons are 1, we know that the total mass is 208. So there are 82 protons. We're guaranteed that because it's lead. That must mean that there are 126 neutrons, and I get that through subtraction. 208 minus 82 leaves 126 mass units that must be neutrons. Sometimes we'll abbreviate it as A, which is the number of protons plus neutrons. Here they are. I've shoved them in the nucleus with the protons. Protons and neutrons both live together in the nucleus. All right, well, so you would think, let's see, 82 protons, and they have a positive 1 charge on them, right? Well, that should be balanced by negative charges of the same amount, 82 negative charges. And that would be true for a neutral atom of lead. It would have the 82 protons because it's lead, and because it's neutral, it would have to be balanced by 82 negatively charged electrons. But this is not a neutral atom of lead. This positive 2 charge out here tells us that it's not balanced. It actually has a net charge on it of +2. So we've got 82 positive charges. That implies that we only have 80 negative charges, because the net was 2 positive charges. You could have a net negative charge on ions also. We'll talk about those. So just make sure that you can calculate the numbers of any of these different particles given this symbol. And a previous time that I taught this course, a student pointed out to me, Hannah, look, when you gave us the symbol, the mass is up top and the atomic number is down low. That's a typical way of writing this. But on the table, that's not the case. I had actually not ever noticed that, but you're right. Here they put the atomic number up higher and the atomic mass down low. Just look, you know that the atomic number must be a smaller number than the mass. So the smaller number here in the table must be the atomic number. So for 10, the 50 is how many protons it has. For lead, the 82. Has to be that way. Now, the interesting thing that shows up here, leading to the next piece, is, now wait a minute, this is 208. Why does the table here have this 207.2? Does that imply a piece of a neutron? And it absolutely does not. So what's going on here is we're about to go through a mathematical exercise of averaging this, okay? So we're going to talk about why we need this decimal involved here at all. All right, so this is going to be the idea of what are called isotopes. Please do read. I'm trying to rush through this, and this video is already getting long. So please do read your textbook so you know what these terms are that we're talking about, and please also do ask anything that I need to to cover again during class. So during class, we are going to do some classwork problems, but that does not mean that you should not be asking questions. It's a wonderful time. You've got me as captive there in the classroom with you. You can ask all your questions. I love for students to ask questions. I want to help explain things. Okay, isotopes. Isotopes are basically different versions. So you saw that lead could have the 208 mass. Well, that's not the only option for lead. It can have other masses as well. Now, we're guaranteed that it had to have the 82 protons because that's the only option for lead. So if there's a different mass number, it must imply that there's a different number of neutrons with it. Now here I'm not going to use lead as our example. I'm going to use hydrogen, make it simpler. So one version of hydrogen has 0 neutrons with it. It's just a proton in the nucleus. And we will call that hydrogen 1. All right, so what's going on here? It's hydrogen, so we know it has 1 proton. But its nucleus only has a mass of 1. So 1 minus the 1 proton, well, that leaves 0 neutrons. So this is all we've got in the nucleus of a hydrogen 1 atom, is just the 1 proton. But it's not the only way that hydrogen comes. There's also a version of hydrogen that does have a neutron in there in the nucleus with it. So now we've got 2 particles in the nucleus, right? So we have a mass of 2. It's still hydrogen, so one of those is a proton. So the other one must be a neutron. That's called hydrogen 2. And actually, there's a third version of hydrogen called hydrogen 3. Sometimes hydrogen 2 is called deuterium, and hydrogen 3 is called tritium. You might have read about that in some science fiction, or maybe even some nuclear chemistry if anybody happens to have read any of that stuff. Tritium is a very highly controlled substance. It's used in nuclear weapons nowadays, and so we control tritium really carefully on the planet. But it is basically just a hydrogen atom that has 2 neutrons in the nucleus. Still hydrogen, so still 1 proton, but it's got 2 neutrons to go with that. So that's what isotopes are, is these different versions of the same element. The only difference is their mass. And so I'm gonna jump back to lead here. So we noticed earlier that it's got this weird, wait a minute, 207.2 as the mass on the table. What's going on with that? Well, it's called a weighted average. Somebody asked me during class to give you, I'll not use the test example here, but I think it might help to explain it to you once we're together in class. But a weighted average says that you take, well, we know that the different isotopes of lead, here I'll point them out, we have lead 204 is naturally occurring, so is 206, 207, 208. Turns out that lead 205 does not occur naturally. But then we got to look at the percentages of them. So if you take all of the naturally occurring lead in the universe, only 1.4% of it is 204 version. 24.1% is the 206 version, 22.1% is the 207 version, and 52.4% is the 208 version. Well, if you take all these percentages and divide by 100%, you actually get this 207.2. So that's what that piece on the table is telling us. This is the 207.2 is the weighted average calculated just like this. I technically calculated this way instead. 1.4% is the same thing as 0.014. So I just go ahead and convert my percentage to a decimal, and then I don't have to worry about dividing by 100%. This is exactly the same calculation and leads to exactly the same result. All right, so remember that you do need your own periodic table. I've seen a lot of good things in past chemistry classes. A lot of folks have like laminated ones and stuff like that, so kind of cool. But just remember that you need your own for the exam, and it's also you can write stuff on it. I don't mind at all. I'm not going to ask you questions that I'm worrying about you having access to a cheat sheet. In fact, we're going to do a cheat sheet and the periodic table, so it's fine for you to write on your cheat sheet and on your periodic table. Here are a couple of examples, but I encourage you to go find your own favorite periodic table. This is kind of a simple one that we used back when I was teaching high school. We used it for the end of course exams. Some of y'all may have trauma from end of course exams, so don't mean to trigger that. But go find you a good periodic table to bring with you to refer to over and over again. All right, last slide for today. So your homework is to make sure you do read through sections 2.3 to 2.7 from the textbook. And I know you already should have read 2.3, but now maybe you'll pick up more of it if you go through. Also, please do watch video lecture 2. I'm interested to hear y'all's approach. I think my approach would be to read first and then watch the lecture. I'm interested to hear if that's the best way for you individually, or if you like doing it the other way around, or how you like consuming it. Let me know. I'm interested to see what works, what maybe works, and then we learn later doesn't. Also, do this, please. Review your maths. So look, we're gonna come back to the math heavy part of chapter 1 next week, particularly in the case of some of the stats. And algebra is always going to be a bear that we're going to have to wrestle with trying to go forward. So do review your maths, preview those stuff. Let me know if you want any help with the maths, and also let me mention the math lab over in Sequoia is a great place to go. They love to help you over there. Some students like that better because it's not like going to a professor's office. It's just going to math lab where there are other students that want to help with the math and sometimes with the chemistry as well. Can't guarantee you there'll be somebody there that can help, but a lot of times there will be, especially for the Gen Chems and Gen Chem 1 in particular. So please do go there and ask them for help and let me know any feedbacks from it. I know a lot of those folks well, and I can tell them stuff that didn't go well or that did go well. So please let me know that. Please do go use your resources. Let me know if you need help finding it. Let me know if I can help you any. If you see any maths coming up, I can help talk you through those as well. So let me know how things are going, and see you this week in class.